Mentions is that at the end, you kind of start off with this abstract problem. But this abstract problem might actually, it's a crude model, as Griffith suggests, for neutrino oscillations. All right, and it's a problem that, you know, this form of this problem shows up everywhere for all types of transitions and oscillations, and so it's a good problem. But let's tackle it. All right. So here we go.
You know, problem 3.8 or example?
Example problem. Example 3.8. Okay, but there's a lot of details in here that we have to go over. So example 3.8. Okay, so he starts with a basis set. Alright, and he defines this basis set the following way. 1 equals 1, 0, and 2 equals 0, 1. Okay? And so this is kind of abstract, alright? But if we were talking about, like, if we were talking, you know, about Cartesian coordinates, this might be I hat, and this might be J hat. So I hat might be 1, 0, and J hat would be 0, 1. Right? So if we were talking about a vector space, and we were talking about the unit vectors, you know, we're talking about a good basis. So essentially, this is a good basis. This is a good basis. It's a good 2D basis. Now, can you imagine any quantum mechanics problems that have a two-dimensional basis? All right, so what you have to see is, you have to think about this. If I have a 2D basis, then that means it spans the whole space of possibilities in 2 dimensions. Right? So what quantum mechanical things come in just 2s?
We looked at the finite well.
Yeah.
The infinite well has n answers, right?
Any dimensions.
I'll give you a hint. Something with an electron?
Yeah. Like an electron has a surface area. It's two-dimensional.
So now you're thinking about actual physical, spatial things. Now think of what we're doing in quantum mechanics.
The electron in a 1D well.
What about an electron? What does an electron just fundamentally have?
Has charge.
It has spin, and what can the spins be?
Up or down.
Up or down. All right? So maybe this is a two-dimensional space where this is spin up and this is spin down. All right? So we have to extend this to some type of abstraction. That this 1, 0 represents spin up, and maybe this is a spin down. Okay, what other things have 2s? Well, you might not know this, but there's this very interesting thing about the connection between protons and neutrons. All right, and protons and neutrons are very closely related to each other. They almost have the same mass. All right, and so at some level of approximation, you can approximate the proton and the neutron as something, all right, a nucleon, and the spin-up nucleon is a proton, and the spin-down nucleon is a neutron. All right, so this might be a basis set for protons and neutrons. Okay.
Spin up as a proton?
Yeah. You know.
Spin down as a neutron.
Yeah. It's called an isospin space. It's not spin as like a spin of electron being up and down. It's a further abstraction. And so in isospin space, the neutron is represented by an up and a proton by down. It's a complete abstraction. All right?
So it has nothing to do with spin?
Nothing to do with intrinsic angular momentum spin of an electron. Or spin of another particle. It's a different spin. It's isospin. All right? It's in a new name. Okay? So this could be a proton or a neutron basis. But it could also be what he suggested as a neutrino oscillation. All right. Now the only problem with that problem is how many neutrinos are there?
Neutrinos come here for play this,
I'm not going anywhere till someone has an answer. How many neutrinos are there, all you particle physicists out there? How many? Okay, if you consider they're antiparticles, yeah. But essentially there's how many families of particles?
Electron neutrinos, tau neutrinos, and muon neutrinos.
That's right, there's 3 families of particles. Every family has an electron, every family has an electron neutrino, and every family has 2 quarks. You guys gotta know this. You guys have been with me long enough. All right, all of you. First generation is the electron neutrino, and the up and down quarks. Second generation is the muon neutrino, and the strange and charmed quark. What's the third generation?
Tau with the
Start with the electron, it's tau,
tau and a tau neutrino,
and then
top and bottom quarks.
quarks. There you go, okay? And so, as Dale mentioned, there's also an antiparticles. But, so, you know, if we're talking maybe an electron, and this might be an electron neutrino, and this might be a muon neutrino, and you kind of forget about the tau neutrino for now with this approximation. Okay, so do you see how this problem is an abstraction of many different physical situations?
Yeah, just real quick. So without like, 'cause I haven't looked at the solution yet,
Yeah?
and I just so the problem is like trying to find out like what is the state at time t.
Right.
All right.
Okay?
So yeah, right.
So that's why I've got to build this for you. Let me give you this. What have we been doing so far for solving Schrödinger's equation? What have we written down first?
Schroeder's time dependent.
Okay, so we've done this. H times psi equals IH partial psi with respect to t. Then what?
And separation of variables, we got g of t equals e to the negative I e n t over h bar.
Okay, then what?
The time independent.
Yep.
Give us addition of the states.
Right? Then what do we do here?
Just, we use separation of variables and assume solutions.
Solve for these things, and these became our infinite, complete
Basis.
basis set. Okay, then what did we do? Constructed a general psi of xt equal
Summation of the n, c of n,
Cn
e to the I e n t over h bar psi of n.
Then what did we do?
Now
Solve
we
for c of n, which
How did we
is
solve for Cn's?
c n equals the integral of psi general of x
use
t equals 0 times psi of n.
And then this is star, right?
Yeah. And then
Psi
dx.
of n dx.
Now we,
Alright.
now we use cats and,
What's that?
now we use cats there, so we don't have to,
Right. So, does it help you if this whole problem is this, but you don't see it? So this whole example problem is this, but it's in this notation. Okay?
Yeah, actually, start yellow.
What's that?
You start with side and not left side. So you did that last time too. I looked it up. It's on page 34.
Okay, what did I do?
You start with the other one. You don't start with the side.
Oh, you started signing. Okay, thank you.
Not the initial.
I thought you were saying starting with signing. That's starting with.
We all think you're a star.
No, yeah, all right. All right, so look, everybody, does everybody feel more comfortable? This is all I'm doing?
Yep.
Okay, so let's do it. All right, now, so the whole thing is that, okay, is that this, right, this is a basis set, right, and it's a good complete basis set, right, it spans the two-dimensional space that my object can live in, a spin up or a spin down, it's in the I hat and the ij, right, but is this the eigenbasis? So this is a great basis, a great complete basis. But is it an eigenbasis? All right? So This is a good basis. This is like, for example, this is like, if you started off with Cartesian coordinates, but you were trying to solve a spherical problem, right? Cartesian coordinates is good, but is it the good coordinate system to use for the spherical basis? No, it isn't, right? Okay, so this is a good basis set, but I haven't solved this yet, okay? So here's what we're going to do. We have to find that good basis. And then once we find that good basis, we're going to do all these tricks.
So the question is like, will we get science back when we use those algorithms?
Hold on 1 second. Say that again, Alan.
I think the question here is, will we get science back when we use those operators? So you want it to be a negative?
Right, and you won't right now. Okay, so in other words, if you put these in, you won't get an Eigen problem. Okay? Okay, so let's do it the following way. So the notation that Griffiths does, and I'll just use size as opposed to s's. But the most general solution, so the most general solution, and again, I'm going to do it like this, psi general, to draw the connection to what we're doing, is equal to A times 1 plus B times 2. What? And that's kind of like this step right here. This is the sum without the time dependence. If you take out the time dependence, it's just a sum, it's a linear combination. The general solution without the time dependence is a linear combination. All right? And what restriction, what has to be true about these projections?
The sum of the squares on equals 1.
Okay, where a squared plus b squared has to equal 1. All right? So the projections of the projections squared are the probabilities that you find yourself in that state. All right, now, the Hamiltonian. Oh, crap.
He wrote that, the book he wrote, the equation also has another matrix, which is just A, B. Because 1 is 1, 0, and 2 is 0, 1. He just rewrote it as A, B.
Okay.
The top of page 121.
No, those are the coefficients.
Yeah, but next to that, you wrote A times 1 plus B times 2 equals...
Oh, I see what you're saying, yeah, in terms of one row of column vector. Okay, but now the Hamiltonian. And here's what I forgot, I wanted to actually start off here, so I'm going to have to do a little bit of a side note because I wanted to talk about the Hamiltonian. The Hamiltonian, he gives us as some generic Hamiltonian that is H, G, G, H.
Now, why would we ever think to do that?
Okay, so first of all, if this is going to be something about like the neutrino, you're going to measure this particle, right, and find out if it's a neutrino, an electron neutrino or a muon neutrino, right? Right, and you're going to measure its energy. So if I want to measure its energy, in this case, the Hamiltonian is for the energy. If I'm going to measure the energy, is that an observable?
Yeah.
Okay, so if it's an observable, what type of Hamiltonian do I need?
Hermitian.
I need a Hermitian Hamiltonian. All right, and what did the Hermitian Hamiltonian say about the elements of the matrix? Remember, Hermitian, H dagger, which equals O dagger, equals O transpose complex conjugate has to equal O.
So the diagonal has to be.
So what does that mean
The
about
diagonal
diagonal
has to
terms?
be, those H's have to be real.
They have to be real, and then, yes, they have to be real.
G's can be either real or complex.
Okay, so real, but they have to, yeah, they can be real or complex, okay?
And that's what makes a Hermitian.
Yes. This is the condition for a Hermitian operator. The operator adjoint equals the operator, and the adjoint means to transpose a complex conjugate.
Operator at, is equal to the?
Yes.
Is that an equal sign for the operator plus equals operator T star?
Yep.
Okay.
Yeah, so this, that's called the adjoint, are these two operations, both of those operations. So you transpose it, complex conjugate it.
So that means if you have a matrix, in order to get the dagger of it,